Hello students, welcome back. Now let's go to section 4, expected value and standard deviation 2. Obviously, this is a continuation from section 3. So let's begin with a review on section 3, especially on expected value. Here we go. Let x be a discrete random variable and p be its mass function. Then the expected value is defined like this. Multiply all the pair of values and associated probability values, and then add them all up. That's the expected value. Alright? Now, let's expand this idea for composite random variables. Here we go. P of x is the probability mass function. The probability that the random variable capital X is taking a real value small x. That's P of x. And then expected value is defined, well, the same way we did before. Now, from here, let's consider another random variable, another discrete random variable, y, but it's not just any random variable, but it was obtained from a composite function, h composition x, where h is a real function, because, x of s is a real number, you see? And then h is a certain real value. Then I'm going to get another random variable, right? Okay. And in this case, it turns out that the expected value of y turns out to be like this, because you see, y value is obtained by h of x, so h of x like this. Does it make sense? Well, it'll make a little bit more sense if you go through an example problem here. Okay, let x be a random variable given like this. 5 red balls, 3 green balls, and 2 blue balls. If red, then I lose $1. Green, then I win $1. And blue, I win $3. Alright? Okay. Calculating the expected value of this x is left to the students. Now, let's consider this random variable. Y is x squared. You see? This composite map H is square function. So whatever x value, capital X value, I square it. What are possible capital X value? -1, +1, and +3. So what are possible values for y? -1 squared, which is 1, +1 squared, which is also 1, and 3 squared, that's 9. Make sense? And, I didn't want to show you that one for z, so okay, let's stop here. So, for x, we have -1, +1, and 3, and the probabilities. And let me call this px. Mass function for capital X is px. Now, for capital Y, I need another character. I cannot use P anymore, it's taken, so let me choose Q. And the random variable Y will take values 119. You see, -1 squared, so that's +1. And 1 squared, that 2 is +1. And 3 squared, so 9. Make sense here? Therefore, actually, I can put these two together like this, 1 or 9. Only two possible values. And then probability for 1 is 1/10. And that one stays as 2/10. Make sense? Because these two will give me the same value. Okay. Now, what if we calculate the expected value of y? Oops, I didn't want to show you that for z, at least not just yet. Okay, let's consider similar thing for z. So this is x minus 2 squared. So what are possible values for z? Capital X can get -1, +1, or 3. So z can take -1 minus 2 squared or +1 minus 2 squared or 3 minus 2 squared, right? Those are possible values for z. And what is -1 minus 2 squared? -3 squared? That's 9, isn't it? Oh, never mind. Hey, how do I undo? Okay, let me get this one back. Let me copy and paste. So -1 minus 2 squared, -3 squared, so that's 9. 1 minus 2 squared, -1 squared, so that's +1. And 3 minus 2 squared, +1 squared, so it's 1. Just like previous example, I have 911 again. Previously 119, so it's a little bit different. 911, okay, alright. Now, what is the probability mass function in this case? That one was for y, and let's look at z. 911, previously 119, this is 911. And then these two actually are the same, indistinguishable as far as z is concerned. So yeah, I can consolidate those two into this. Compare that with previous problem here. Consolidate these two into this. Can I put everything in the same viewing window? Okay, now. So here, that's for y. Okay, alright, barely in. Here for y, and there for z. Please stop the playback if necessary, and then make sure you're understanding this. Okay, alright. Now let's calculate the expected values. No problem for expected value of x. Let me see. Copy and paste this thing. Alright, multiply, 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 and add them all up, and that's it. Alright. Now how about this? I could keep this whole thing, same probability, 0.5, 0.3, 0.2 for capital X, and then I can consider -1 squared. As a matter of fact, this part would have been better, -1 squared. And then this one, +1 squared, and that for green. So here, in the x part, we apply the square function. That's one way to do it. Like this. Or another way to do it is to go back to this probability mass function of y down here, and then go directly 1 times 1/8, 9 times 2/10, and then add them all up. Do you get the same thing? Always you get the same thing, because this one, it's okay to decompose them into this red case and green case, because same value here, same y value there, and then 0.5 plus 0.3 is 0.8, so no problem there, they're always the same. So whether you calculate directly from the mass function of y, or you calculate from x using, h composite s square function, you get the same thing. Now how about this? Shouldn't be x minus 2 squared actually, sorry about that, that's a typo. So now as for z, I can do x minus 2 squared, that function. So here, negative 1 minus 2 squared, that's for red because I'm doing x minus 2 squared. And this one, positive 1 minus 2 squared, that's for green ball. And then this one is 3 minus 2 squared. And then this is 9. And this is 1. Either way you get 5.0. Or, let's see, where's the mass function for z directly? Here, copy and paste that. Do it directly. Multiply, and add them all up. Wait a minute, it's 0.5. Sorry about that, this is typo. I'll correct that. So 5 red balls, and then 5 either green or blue balls together, because there's no difference between green or blue. So directly we can calculate like this from the mass function of z, or you can calculate from x because z is defined by x minus 2 squared. So for x we have red, green, blue, all of those. Because for x they're all different. For z, there's no distinction between green and blue, so I could consolidate and we get this computation. But for x, there's difference between the one and the other, so I have to keep those. And then for payoff values, I have to do x minus 2 squared, x minus 2 squared, x minus 2 squared to all those values. Is there a difference between those two? Not really, because payoff values are the same for these two guys, 1. And then if I add up the probabilities, and it's 0.5, so it's same as this. So, what is the conclusion here? If you get another random variable by a composite function, whether you got as a square, x square, or x minus 2 quantity square, or even more complicated expression, who cares? Whenever we have composite expression there, all I have to do is put that composite expression over here in the definition of this expected value in place of this guy right over here, which I just highlighted in red, into this. Then I'm going to get the expected value of that composite random variable. Yes, I admit it's a bit confusing, but there you go. So you can do either this way or, from here to there, like this, for composite case, or get the mass function of y, do it hard way, get everything, consider everything, and then recalculate the mass function for y. Either way, you're going to get the same thing. So why do we do it in much harder way? Get everything for y, recalculate everything for y, and simplify. Why do we do that? They're going to be the same, so let's take the simpler path. From this expected value expression, we'll simply take composite function. Whether it was x squared expression or x minus 2 squared expression, or something still different, like this. For variance, same probability, but here I get x minus mu squared. So it's the same as expected value of capital X minus mu squared. So consider this part as a composite random variable. So we can express variance as an expected value of this random variable, which actually is associated to the previous original random variable, but of course not the same. Same for standard deviation. Expected value of this square random variable, and then we take the square root. So standard deviation needs final square root, so it's more complicated. So most of the time in this composite expected value expression, we just calculate or we just look for variances. And then when standard deviation becomes necessary, we just take square root and that's it. So most of the time you're going to study variance. So using that, we can state and prove some properties of expected values and variances. Here we go. Expected value of ax plus b is equal to a times the expected value of x plus b. This is composite random variable. Say capital Y is ax plus b, you can get like that. And then you can, of course, find out this capital Y using a and b values and this x, get its probability mass function all straightened out, and then recalculate everything and simplify. You can do it like that. Or you can go directly with capital X, and that turns out to be much simpler. For variance, like this plus b part drops out. This part is squared, and that makes a lot of sense because variance itself requires squaring. And standard deviation, if you take square root of a squared, then you get absolute value of a because a can be negative, so I have to keep it positive, so we need absolute value there. Otherwise, square root and square cancel each other out. And finally, we have this expression. Variance turns out to be expected value of x squared minus square of the expected value. This should have been capital X. So many typos, sorry about that. Alright, and then we have another expected value expression. Let's see. If you take the random variable z by this expression, x minus mu over z, then that new random variable z has expected value 0 and standard deviation 1. Well, actually, it would have been a bit easier if it is variance equal to 1, but you see no difference there because variance is 1. Take the square root, then square root of 1 is 1. So standard deviation of z is 1. That means the same thing. Now, well, it's the same thing, so let me just keep it at that. So another way to do the same thing is like this. Expected value of x minus mu over sigma is 0. Variance of this quantity is equal to 1. Same thing. So this is a manipulation that will get a new random variable closely related to x, but some nicer property. The mean is 0, expected value is 0, and the variance is 1. And if you look at this expression here, you can see that this is a kind of like scaling. X minus mu, so adjust the 0 point a little bit and then scale with this. This resembles the change of temperature. Scaling of a temperature from Fahrenheit to Celsius, for example. So x minus 32 divided by 1.8, then you get Celsius temperature. So basically x and z mean the same thing, just different scale. That's how they are related.